Yeah. So hi, I'm Hemant. As ma'am has given a very good introduction, I currently work at Morgan Chase. I worked with Madhuri ma'am before on other projects. The what I'm going to present today in today's session is you can think of it as an introduction to blockchain, and you can think of it as a high-level view of the concepts that we will explore in far more detail in the coming sessions that you will attend throughout the course of this FTP. So, without further ado, let's start. So, I'm just switching off my camera to conserve bandwidth from my end. But please feel free to ask any questions in the middle. I will monitor the chat in between to see if any questions are there. Yeah, so let's move forward. So, in the coming, maybe not 2 hours, but in the coming session, we'll have a look at a sort of holistic view of how did we get here? How did we get to the idea of blockchain? Why did we need to get to this point? And what are the things that have led to this place? The main things that we have to consider are that if you don't know much about the history of what are financial transactions, that the different ways in which we were started to record financial transactions, what are the different drawbacks or what are the different problems with that approach, and why we have approached towards blockchain. That's largely the first 10-15 minutes I'll do that. Trust me, that might seem a bit, why am I learning all this GK? But it really helps in understanding the mindset of why this was developed. Then we look at, what does blockchain do that's so different? Then the benefits and uses of using blockchain in especially we will look at financial transactions in this, but blockchain has multiple applications as well. What does the blockchain consist of? And finally, we'll look at how hashing functions are used in blockchain. It's almost a core component of blockchain. So we'll just take a look at that. The next session will cover this in far more detail as well. So yeah, as I said, you really don't know, you really can't stand on what you're doing now if you don't know why you've reached here. So that's why it's really important just take a look at history. So if you can think of that. Now we have come so far in our method of bookkeeping, and from a paper or from a static bookkeeping to a digital era bookkeeping. How are we transitioning to that? So that is the main application of blockchain, right? So let's hop into our time machine and just take a look back at some points in history to understand where we've come from in terms of recording financial transactions and stuff like that. So here you have the oldest recorded transaction that has happened. We have arrived in this is the Mesopotamian civilization, modern day Iraq, where you can see here on the left side that this is a cuneiform tablet which is a clay tablet where they have recorded some transactions. So this is literally the first written sample we have of a financial transaction. This is from the 4th millennium BC. So these are, it's something that the civilization from its start has required. So for that point of time, yeah, a stone tablet was fine for usage in those scenarios. But then, as you know, with any job market or anything like that, the first thing that you encounter is a customer complaint. So the entire full circle existed in Mesopotamia at that time. So this is some sample that somebody has found where there were at that time trading of precious metals was a big deal. So copper ingots was sold, and that was of inferior quality. And these two, the seller and the buyer, are having a quarrel here, where if the seller says that if you don't want them, don't buy it. And then the buyer is saying that you can't speak to me like that. Whatever. So this is an actual existing artifact where so we have the entire circle here. We have the accountability from the financial transaction and the record of the financial transaction itself. So really, where we are today is not that different from where we were many years ago. So just a fun look at that. Going forward, then coming back to our motherland, India, we have here you can see Chanakya. So this is around the Mauryan time. So I think 300 BC. So at that time, there was a pressing need for better management of the empire and better management of finances. And at that time, the palm leaf books were used to record all of these transactions. And palm leaves had a slightly better, it's easier to transport, it's easier to string into a book and keep a lot of information in one place. Imagine having a book of stone tablets, not possible. So a palm leaf book really, gave a bit more edge to it and a bit more usage to an old financial, an old method of recording financial transactions. But we all know that these even these palm leaf books, they have to be kept in very good condition. And actually, I've seen some of these when I've these old restored palm leaf books. They are very easy to be destroyed. So then we came to paper. So when the Egyptians invented paper around 3rd century AD, the method of bookkeeping had also advanced. So first, obviously, paper provides you even more portability than a palm leaf book and more durability. But going forward, the requirement for financial transactions became simply more than, okay, I bought this good, sold it to this person. More than that, it became a sort of maintenance as we do today. So this picture that you see on the right, this is a real story where there's a man named Erroneous, where he kept an archive of all the transactions involved in the running of this estate. This is just a sample picture of an estate. How much did the bed cost? How much did the roof tiling cost? How much does it cost to buy food every day? So think of it as a manager of a hotel. Those kind of transactions have also been recorded. So the requirement of financial transactions becomes more and more prominent in the society as the years go by. Now coming to the real, sort of godfather of every single CA in the world, which is Luca Pacioli. He's actually a mathematician, and for the very first time, he was the guy to record the fact that that we have an account that has a credit and a debit concept in it, meaning the money comes in, money goes out sort of way. So the double entry bookkeeping is something that he introduced, and it's pretty much what anything that we use, any financial transaction, any financial market that we deploy, that we use today. The basic concept is the concept of debit and credit. So this man is very famous, and he also has a stamp in his name to commemorate his effectiveness. I see some chats. I just wanted to check if that is anything relevant. I think there's questions about the session. Okay. Please drop any questions. I'll keep checking the chat. So anyway, here I don't think you may have many questions. Luca Pacioli, very important figure in financial bookkeeping. Moving forward. So right now we've looked at multiple examples of essentially what you would call a centralized ledger system. Meaning, let's take the case of Luca Pacioli. Let's say he was running some government institution. If he was running, let's say any transaction that happens, it gets entered into one ledger or one set of ledgers. So the problem, there are some inherent problems with a centralized ledger system, which is meaningly that you have to trust the person that is handling that centralized ledger system, because that ledger is not available for us to always see. It's not something that is completely visible to us at all times. So we just have to trust that is done correctly. And you don't need reminding how the sort of mistrust in any centralized system is pervading our society nowadays, right? All from the simplest example you can see is how people, they don't trust the result of election. They don't trust the validity of financial transactions. There's so much wire fraud going on. So the main thing here is that because if you take elections, there is a centralized authority that is trusted to handle the votes in a trustworthy way, in a valid way, in an honest way. But I mean that inherently there is an element of trust that we must have with the person that is handling our data. So that is something that as we go more and more into this information age, where there's data is available at all places, and we are freely sharing our data with other people, the confidence has to be built in a system where you can say that, okay, my data is going to be transferred in a safe way, secure way, and nobody can tamper it on the way there. So this is where the sort of distrust comes into centralized ledger system. Another sort of con that I see of a centralized ledger system is what I can show here of an example. This is a fairly common example, I would say, of where there are two siblings. So I think the left one is called Hannah, the right one, I don't know, maybe let's call him Connor or something. So so basically there's a piece of land that both of them are holding a stake to. Now Hannah claims that it's hers, and Connor claims that it's his. So to prove that this land is theirs, obviously you would already guess you have to show land records to say that who's the original owner and all that. So Anna would go to either a lawyer or to go to a land agent or somebody like that, and find out, okay, what is the history of this land throughout? Because he also has to prove that the brother has never owned it at some point, right? So she first finds out, okay, who is the original owner? So as some Adam is bought it from Mary, so the current owner is Adam in the year 1900. Then in 1930, Dave has bought a piece of land from Adam. Dave becomes the owner. Then Anne, who's our protagonist here, buys that land from Dave, so the current owner is Anne. So in present day, owner is Anne. And this is how she would prove it. But to do any of this, your exposure and risk in terms of, whether you would, any data leakage or anything like that is pretty low, because, all the documents are secured and everything like that. That's fine. But the main thing that you would expend of your own is your time and money, because none of this, if any of you have gone into land negotiations and stuff, it's a very, very sticky business where you have to, you have to spend, lots of time, lots of money on a land agent, on any kind of, contacting a middleman, basically. So what if we could, cut out the middleman in between all of these, right? And ensure that the transaction or whatever we need to do with the system can be done by ourselves and is visible to all, thus building more trust. Another problem is that, as I said earlier, the mistrust is inherent in this, where both siblings don't trust each other. So the burden of proof that each has to present becomes more and more because of the mistrust that exists inherently in the system. So the land agent will be, you'll pay more and more and more because of the inherent mistrust that exists in the system. So this is where, the sort of idea is that, what if we could cut out the middleman and make sure that any data or any transaction that I want to prove is mine, why do I need a middleman? Like, it's my data, right? So why do I need a middleman? Why do I need to go through all these procedures? What if it was much easier to access? So, and that is conveniently where we come to our idea of what if there was a blockchain where you say that, these are my land records blockchain. And then that data is available to everybody. So you know exactly who is the owner. There's absolutely no chance of a dispute because the validity of the blockchain is almost unquestionable because of it. We'll come to the reasons for that. But the validity of a blockchain is verified by multiple participants, not just a single participant that exists in a centralized system. So that is conveniently where we come to a blockchain, where this is another main drawback of a centralized ledger system, which could be solved by a decentralized or a distributed ledger system. And that brings us neatly to a prelude to blockchain. So here in this, we will look at, think of it as, we are sort of breaking ground and we don't really know what a blockchain is. We just know that we want a distributed ledger now because we have discussed the issues with a centralized ledger. So if you want to create a distributed ledger, what are the things that we need to keep in mind? What are the sort of common pitfalls we could fall into. So this is just a look at that. So we'll take a look at that in the next part of this presentation. So here we have 4 people, and we are trying to implement a public distributed ledger to handle the financial transactions. We're just going to look at simple things like, point A sends money to point B, person A sends money to person B sort of scenario we will look at here. So we have Asha, Mariam, Arun, and Ali. So we have 4 people. So we have, as you can see here, we are going to maintain a public ledger of any transaction that is made. Like we showed in the previous example where, the transfer of ownership of the property, right? Similarly, we will show here that, Asha is paying Mariam, Mariam is paying Arun, Arun is paying Ali, and so on. So we know the amounts of money that are being paid and who is being paid by whom. That is basically what we were looking for, right? We wanted to know the chain of custody sort of thing of the money being exchanged hands here. So that seems to be neatly accomplished by this ledger. Now, what could be a problem that could occur here? If you can either put it in the chat or you can think of any issues. I'll just wait for a second. What problems do you think could occur from just recording the transactions alone? Okay, I'm looking at the chat. Okay, I don't see any answers there. So, okay, before we go on to the problem section, okay, there seems to be some answers. Yes, anyone can refuse. That's true. That is, I mean, let's assume in this scenario that the transactions are accepted by both parties. We will come to that scenario later. That's actually right. So rather than acknowledging the payment, the main problem here is that you could initiate fraudulent transactions, right? Because what happens is, so before we come to the actual problem, the main structure here is that, like we said earlier, instead of going to a central authority and finding out, oh, this is the land document, this is the whatever, each of the participating people, I'll call them nodes, they all maintain a copy of the ledger, which is this one decentralized ledger that we have. So all of them have access to these transaction data. In a real world scenario, what will happen is we won't know that a particular wallet belongs to Asha. This is just to show. So there will be like a wallet ID that is attributed to Asha, but I mean let's abstract that portion for now. So we'll have a record in each. So each guy will have one copy of the entire ledger. So the non-acknowledgement of payment, that will come as part of the initiation of transaction. That's fine. But fraudulent transaction is one main thing. We'll tackle that later. But something even far more simpler than that is what I was looking for. So anyway, I'll go forward from here, which is the main problem that would exist here is that I could, as you can see here on the left, where the prices that the person is the money that is changing hands. So what could happen, because each of these participating nodes has the authority to add a transaction to the blockchain, right? Okay, let's consider a ledger for now. Don't call it a blockchain. To the ledger, we can add a transaction. So there needs to be some checks and balances to see how much money can be transacted by a particular person. Like you can see here, the Arun has decided that, okay, I'm just going to say that I'm paying off all of the people that I owe money to, and then just completely disappear. So what do we do in that situation where a node just says, okay, these are my transactions, and just disappears? So there is a different concept of consensus mechanism where rogue nodes are removed, but let's not go to that. So if you are doing an overdraft, essentially what Arun is doing is an overdraft. He's claiming to pay more money than he has as his balance. So the obvious solution to any of this is to preserve your own balance within the chain, right? So for each of these participating nodes, we actually maintain the balance that exists with that particular wallet. So and this information is generally available publicly. You can see what what each wallet, what is the amount of money that they, or not, I wouldn't say money, the number of coins or number of units of that particular chain that they have, and you can see that publicly. So before a transaction can be initiated, the first thing that you do is to check if that person has enough balance or has provided enough proof of their balance to execute the same. In how it's implemented in Bitcoin is a little different. What happens is, instead of always maintaining a balance, the person who wants to send money to another person has to provide some proof to show that I am able to pay for this particular transaction. So they have to provide proof of past transactions, and then they can execute. But essentially, the concept is the same. Instead of maintaining a static balance, they generate it from the previous transaction. But that is how, in a distributed ledger system that we are trying to develop now, the problem of a overdraft or overspending is solved. So that is the sort of first problem that we have. Now, another problem that can exist. So yeah, this is just the explanation of how do we make sure that we avoid this overdrafting problem, which is you maintain the balance. Always maintain the balance, so you know exactly when somebody is doing something that is out of their means. So that is the main thing. Another problem that can exist is actually sort of what you alluded to. I don't remember the names of the people, but with a good catch, which is, what you were talking about is whether somebody would acknowledge the payment. So before that itself, before we say that, okay, this is a valid transaction, we need to make sure it's valid, right? Then only we can ask the sender to say whether to acknowledge or not. So first we need to make sure that, the transaction that is being added to the chain, whether it is a verified transaction or not. So what can happen is, if there is no verification that is done in this chain, what will happen? Arun is our rogue node here. What can happen is Arun can just, he knows now, because all the quantity of coins that Mariam or Asha or Ali own is available publicly, as we showed, to solve the previous overdrafting problem. So all of the participating nodes having a copy of this distributed ledger, they can all see how much money that the other guy has. So they know that if they add a rogue transaction or a faulty transaction, which is within the limit, and sends money to them, that transaction would get verified. So like you see here, so we know that, so because of the maintenance of balance, we can say here that, okay, because Asha has paid Mariam 3,000 in this world state, the 3,000 is the amount of money that Mariam has. Now Mariam has paid a legitimate transaction to Arun, saying that 2,000 rupees payment has been done. But what Arun knows is that she has 3,000 rupees with her. So 2,000 she has spent, so 1,000 will still remain. So Arun could add a rogue transaction and say that I want to and initiate 1,000 rupee transaction as well. So how do you add a check and balance here? So how that part is done, I'll give a couple of minutes to just think of, maybe if I can get something in the chat. Let's see if someone can get the answer. So how do you say, okay, how do you say that is an invalid transaction? A simple way. Don't think of hashing or anything like that. But in a simple way, how do you say that is not a valid transaction? Yeah, I'll wait for about 10 seconds. If I don't get an answer, I will move forward. Please drop your thoughts in the chat. Like this is a very good point that Dr. Mohan has made, which is that if someone refuses the payment, that will come. So by checking for source of initiation of transaction, yes, but see what happens is that because the data of the so Mariam's public wallet ID is visible to everybody. So in the current state that we have not described any way of checking it, right? So how do we say that particular transaction is invalid? So checking source of initiation of transaction is correct, but slightly off, which is who should have the power to initiate the transaction? Is it the sender or the receiver? So here, Mariam is the sender, Arun is the receiver. So who should be able to verify if the transaction is valid or not? Actually, no, it's not in this scenario. The receiver is the guy who is the rogue node. He is trying to say that he's trying to initiate a he's trying to say that I have received money from this person and tries to get the money from that guy, from this lady, Mariam. So this is so in this case, anytime you now think of yourself as when you're a bank, when you're trying to write a check to somebody in the bank via your normal financial services, you are the one who verifies that and says that no, this is the transaction I want to make to so and so, and you sign the check. No, saying that I am sending money to so and so person. So actually, Mariam is the person who has to sign the transaction and say that this is my transaction. I am saying this is verified. So receiver can generate stamp to attach to transaction. Receiver. Okay. It's not a stamp, just like a public-private key thing that I'll explain in the coming slides. But yeah, that's sort of right. So anyway, let me move forward. Thank you for the participation, everyone. So yeah, this is where we end up at. So a digital signature is essentially what will happen. I have given a sample of your signature is to relate to the concept of a check, where if Asha wants to pay Mariam, Asha has to say that I am saying I want to transfer this money to this person. So that way, every transaction is signed by the sender and then can be verified by the receiver. That verification by the receiver part we'll explain in the public key cryptography portion. So a small part is there in this slide. There's a full session on it in the next one as well. We'll explain it there. So this is how that whole rogue node concept is solved. Okay. Then so that is how that rogue node. So if a rogue node is saying, okay, this 1,000 rupee transaction, I don't want this 1,000 rupee transaction that this Arun is trying to initiate here will not go through, because only Mariam is only allowed for a 2,000 rupee transaction. The 1,000 rupee transaction will not be allowed to go through. So that is now Arun has been foiled here. So now the next thing that our rogue node Arun tries to do is that he knows that the 2,000 rupee transaction Mariam has approved for the value. Let's assume that Mariam has a higher balance than this. So let's say Mariam has a 5,000 rupee balance. Ignore this. So if Mariam has a 5,000 rupee balance and she's paid 2,000 to Arun, she still has 3,000 left. Now in that 3,000 left, Arun, what does he do? He knows that the verified transaction of 2,000 rupees exists in the blockchain. He duplicates the block. It says, I am going to, this 2,000 rupee transaction also, I want to be added to the ledger. And he says, this is a valid transaction because she has signed for it earlier. Now, this is obviously a problem. So how do you make sure that each transaction is different? Let's see if some responses. I'm waiting in the chat. So just think of how would you make sure that each transaction is different. Okay, nonce value. Okay, somebody knows a bit about blockchain. The nonce value is not correct. Nonce value is what you use to generate the hash. That will come later. Timestamp is not good enough because even the timestamp can just be. So essentially, each of these nodes has the capability to add a block to or a entry to the ledger. So Arun might as well just entirely copy the previous transaction and paste it below. So if the timestamp, everything would be the same. So then it would be difficult to distinguish the two things. So timestamp is not enough. Nonce value is not fully correct because nonce is not the only thing that becomes part of the block that then becomes a unique key, the unique value for that transaction. But yeah, that's a good point, Sandeep. So yeah, okay, I don't see any other messages. Anyway, yeah, the easiest way to do it is, so Tanpreet is sort of on the right track, but a little further ahead of us. which is that so the idea is that you have a digital signature plus a message ID. So message ID will make sure that for this particular transaction, there is a unique key. And for this particular transaction, there is a separate unique key. So there is this 1 digit difference. That is just to show here as a sample. So if Arun tries to copy a previous transaction and paste it below, the values that are, there is, each transaction gets a different ID. So because each transaction has a different ID, the previous transaction signature does not stay valid for the signature of the next transaction. So that's how we solve this issue of a rogue node giving us duplicate transactions or copy transactions of the previous instance. So that it was the sort of now we've given a relatively simple or overview of what constitutes a blockchain implementation and what are the things that we need to sort of look out for and how distributed ledgers solve issues that we just discussed, the overdrafting and all those kind of things. So now coming to what one of the participants has mentioned, which is the nonce and all that stuff, that we've actually come to towards the end. But the basics of all of this, which is how did we get this number? What is this number, and how can I say so confidently that for every transaction that value will be different? So that is where we come to cryptography and hashing. So before we go into how it's implemented in blockchain, I will put this up and let's get some participation from you guys. So I think some of you might be a bit aware of how hashing is used in to save your passwords on your database, or how any of these services where you provide your password, how they save it on the database. So if you're aware, you can put it in the chat. How this works. I'll explain it anyway for the benefit of others as well. So we have a scenario here, right? Where let's take Gmail, where somebody's voice is coming through. It would be good if you could go on mute. Or is it? Or if somebody's speakers are on and the echo is coming through, I don't know. Mudiyala Sivareddy, I think his voice is coming. Could you mute yourself, please? Okay, yeah, I'll do it. The organizers to do that. Anyway. Yeah, so we have a sample, let's say we've opened up Gmail, we enter the username, which would be our email ID, and the password. So how do under the hood, how do web services actually save our password on the database? You can put your thoughts in the chat. Okay, I don't see anything in the chat. Anyway, I mean, you may not be aware. That's fine. It's quite an easy explanation. Let's try to go through this together. So, yeah, it's getting quite annoying. Could somebody please mute the participants? All right, let me try if I can do it. Okay, I don't think I have access. Anyway, yeah. So, how you save the password on your how these web services and all. If you're making any backend where you have to save a password, it's never recommended to save the password in the plain text, obviously, because as the owner of an app, let's say I'm making a website where you log in and you're able to see some cat pictures or something. I don't know. So then I don't want to be saving your password. That's not something that any major tech company, they never save your password, which is why you have a forgot your password button where you have to generate your new password. They never save your password. What they instead do is they save a hash of the password. So in the next session, they will actually cover, what are the properties of a cryptographic hashing function. But I'll give you a simple example, which is, so here you have this password QWE12, right? So you pass it through a function, which is a mathematical function. What it does is, it always spits out a fixed length string. So if you take SHA-256, which is a pretty common hashing algorithm, which is used by a lot of these password libraries you'll find on your various programming languages, they will give you a 64 character length string. And that string is going to be absolutely the same for your for whatever hash you give it. So you can change that based on, can provide a secret and add a salt and all of those things. I won't go into that. I'll leave that to your own homework. So a lot of people, they add a thing called a salt to a hash to make sure that it is always unique and nobody can create a lookup table and all that. But basically, you pass a hash through this function which you see here, and you get a unique hash all the time. Meaning, if I change this QWE13, if I make it, it will spit out a different hash altogether. But if I change it back to QWE12, it will give me the same hash as it was before. So when you registered on Gmail and you said that, yes, this is my password, and you told Gmail to save it, Gmail does not save QWE12. Instead, what Gmail does is it saves the hashed version of it and saves that as your entry. So it says, hemant.whatever@gmail.com. That person's password should match with this hash. And when we want to verify, or when I try to log in, basically, when I send the password from my client through to Gmail, they hash it. They hash the password and they compare the hash of that, what I typed in, with the hash of what is saved in the database. And because the hash function always spits out the same hash when you give it the same string. Okay, even I got muted. Yeah. So because the hash is always going to is always going to be the same for the same string that is given as input, we can be absolutely sure that we can compare just the hashes and find out if it's the valid login or not. That's how hashing is used very commonly in any kind of web login sort of service. Just a look at that. Now, what is public key cryptography? So before you read through all of this example, let's consider a simple example of so there are actually two kinds of encryptions that are available. There are symmetric encryptions and asymmetric encryptions. So actually, asymmetric encryptions is what we generally refer to as and use as public key cryptography. But let's take an example of a symmetric encryption. So it's pretty simple. You would have actually seen it yourself as well. I have a zip file or a RAR file or something, and I send it to you. I only want you to open it. I don't want other people to open it. So RAR files have this property where you can give it a password, right? Similarly, I think even PDF files have a property where you can give it a password. So what I'll do is I'll share that file over mail or something to you, and I'll send the password to you. Maybe I'll tell it to you by word of mouth, or maybe I'll put it on WhatsApp or something and send it to you. I think that, okay, that is very safe and only you will be able to access. The problem is that there are so many different kinds of attacks that can happen on these kind of channels, and this kind of details can be leaked. And now once that password gets leaked, you're pretty much in hot water. You can't do anything, because if a malicious actor can get hold of your password, of that one password you've set for your file, that data is immediately gone. It's leaked. So that is the main issue that you have with symmetric encryption, which is what is called a symmetric encryption, where there is a single key essentially. So think of it as a lock where one key always fits the lock, and you have that one key. You give you lock it. You give the file to the other person, and the other person has a copy of that same key, and they put in the lock. They open the file, and they're able to see the data. That is symmetric encryption. So the problem, obviously, as just explained, is this. Now, the solution or the sort of better way of encrypting your data and sending it across is this public-private concept. So what happens is, so there is a algorithm called RSA. I don't remember. The RSA is the initials of three of the guys who came up with it. I don't remember the names now, but everybody calls it RSA. So what RSA does is it uses this. It's very interesting reading, by the way. So if you're, I think in the next session, part of it will be covered, but to really understand the maths behind it, you can watch a couple of YouTube videos and things like that. What they actually do is very, very interesting, which is how do you make sure that every public-private key pair is only is unique and it can never be replicated again across how many ever public-private key pairs that you generate. So how they do that is they use this one mathematical concept, which is that you take any number, okay, any number you take, and you convert them into their prime factors. So, for example, if you take the number 10, the prime factors for that would be 5 into 2. And if you take the number 11, it's 1 into 11, or just 11. Then if you take 12, it's 2 into 2 into 3. So that signature that defines a particular number is never going to be the same for two different numbers. It's always unique. So that concept of prime factorization of a number always being unique is actually what is used internally by RSA. So I won't go into the math of that because that will take like another 30 minutes just to explain. So just think of it this way, that keep it in your mind that this public-private key pair, they are always unique every time you generate it, and the public key and the private key have an intrinsic relationship with each other, where the public key can be used to encrypt something, the private key can be used to decrypt something. Okay, so we actually use the pair of keys is provided to each and every node in our, or each and every participant in our blockchain or wherever. So if a person wants to send something to another person, what happens is I need to know who to send to, right? So that becomes a public key. Public key, as the name says, is visible to everybody. So if person A, B, C, D, whoever is there in the world, they have a public key. Think of it like your address. If somebody wants to send you a mail, you need to tell them your address, right? So that is your address. You tell it to everybody. The private key you must keep under lock and key. You should not give to anybody. You have to keep it with yourself only. Then, so now you have these two keys with you. You want to send a file. So I have my friend is let's say Rahul, my friend. Please mute yourself if you're not speaking. So I want to send my file to, I have a very sensitive file. I want to send it to another person. What do? So I know that I have to send it to so-and-so person. So I know their public key. They know my public key. So what Rahul does is he says that, okay, you guys want to send files to me? Cool. This is my public key. Use this public key to lock your files. Okay? Send it. And so when send happens, it's essentially a broadcast. Every single node knows, right, that the transaction has happened. That's what we just showed with the decentralized ledger example. So every single person just gets a blast saying that, Hemant is trying to send a file to this person. And it just goes through. So everybody will try to unlock it. So if they try to unlock it, the unlocking, as I said, can only be done by a private key. So everybody will try their private key in the lock if they want to be malicious. If they try to unlock my file, because the public key of Rahul was used to lock it, the unlocking can only be done by the private key of Rahul. Nobody else can unlock it. Even I can't unlock it. That's how the secure transaction is done with the public key cryptography. I don't want to go through the slides in that way. I wanted to imagine this scenario, and then you can see how it's so useful in any kind of transaction where nobody in the middle can interrupt the transaction. Only the person who's intended to get the message will be able to get the message. So that is essentially what is happening. So, signature algorithm, private key it's passed through a private key. This is where the sender side, they unlock it with their private key. That's essentially what is happening here in this image. I wanted you to get that whole idea of, why did we get to this point? So, yeah, I mean, this is again sort of how it's applied to the ledger, but I'll stop here. I know I've just thrown a lot of information at you. So please tell me if you want anything explained again, or if you have any questions, please put it in the chat. I will wait for about 2 minutes. So anyway, while you want to put any points up, you can put it up in the chat. I've kept it open, so I will keep looking at it. So the ledger, what you have, as we showed in the previous example, anybody who wants to unlock the message, which is if Asha wants to pay Mariam, only Miriam should be able to unlock the transaction and add, say that, okay, this is I want to verify this transaction. They will verify all of that. So somebody mentioned in the chat earlier, they don't know what if we just ask the sender to verify, the receiver to verify it. So this is essentially how that happens. They verify if the transaction is meant for them, and then they go forward from there. So that is where your private key part comes in. So that is a very rough look at how it gets applied in a blockchain scenario, or in our case where we are showing a distributed ledger. So always the private key of that person only can unlock it. Think of it as if you guys have bank lockers, then your bank locker Tala will only open if you have the bank has one key and you have the other key. So the key that you possess is your private key. The bank's key is the public key. So the public key, it's not as public as this, but think of it as, the bank has that one key which fits all of the locks, but it won't open it. It will only open it halfway. Then your key only can open the rest of the way. So that is essentially the whole property. So if you're really interested, there are like a couple of videos that explain, RSA in great detail, and it's a very interesting concept. If you're, interested in math, nothing like it. Okay, I don't see any questions.
Mr. Hemant, if I can ask one question to you.
Yeah, please go ahead.
So in the previous slides, you showed that how we can prevent the receiver from going rogue, because we said that sender will digitally sign the transaction.
Yeah.
I wanted to know, what if the opposite happens? Let's say sender has the amount. So he or she inserts a rogue transaction. Actually, that payment has not been done. So in that case, how we can prevent that kind of scenario?
So let's see if I understand the question correctly. So there is a person A who is saying that I am paying to some X amount of rupees to person B, but that transaction is faulty. So it's faulty in what way? Like, is that what are you saying? The balance is not available to that person, or the transaction never went through?
Yes, the second case, transaction never went
through. Okay.
Yes.
So think of it.
Can that happen in the first place? That he claims and the transaction never happened.
So there are some cases where that can happen, which is if the sender is so largely that happens if that transaction has been invalidated by the other node saying that this is a rogue transaction. So if there is a malicious actor, they can remove. But generally, what happens if you initiated a transaction, it goes through a set of processes where you try to add it to the chain. Once it's added to the chain, it doesn't get removed. So that procedure I'll come to after this. But to answer your question in a short way, basically, before it gets added to this immutable chain that we maintain, which is our ledger, there is a set of processes that it has to go through. Then only it gets accepted. So when it comes to that, I'll explain. If you still feel I have not answered the question fully after that, please ask again. I'll explain again.
Okay, sure. Thank you. Yes.
Yeah. Any other questions? Please feel free to ask. You can unmute yourself like the participant has just done. Otherwise, you can put in the chat also. I've kept the chat window open. So, any doubts with public key cryptography? Okay, I don't think there is. So please put it in the. Please feel free to interrupt me at any point. You can ask me a question, no problem. I will try to answer it. So this is just again further description of because the digitally signed document has been locked to the public key. It can only be unlocked by the private key. It's just a more better graphic representation of the same. So I will move on from this and try to come to this. So components of a blockchain. So what are the things that what is the fundamental component of a blockchain? That's what we look at. And this is sort of where we come closer to solving that. Please note yourself if you're not talking. Thank you. Yeah. So now we come to what are the different things that every blockchain has. So you would have already guessed from the name of blockchain that a block is the fundamental quantity or a fundamental unit that you have in a blockchain. So every block has 4 things in any blockchain you pick, it will basically have four things. One is the date. Please mute yourself. Whoever this is. Thank you. So you have data. Okay. Yes. Sorry about that. So there are four things that every block has, which is the data that is supposed to encode, which as we showed in our previous examples, would be your financial transaction data. The nonce, which somebody mentioned in the chat, we'll explain what a nonce is. Don't worry. The hash, which is generated, we just showed how hashes are generated in the previous section. We look at how the hash is used in the blockchain, and the previous hash. So we'll explain that. But previous hash, as you might think, is the hash of the previous block. So why do we need that? We'll explain throughout this. So let's look at the first component. Pretty simple, straightforward. We'll have a sender's address, receiver's address, and transaction amount stored in the blockchain. Simple as that. Let's consider the fact where every transaction gets its own block. That's not how it generally happens, but for simplicity's sake, let's do that. So we'll know who is the sending wallet, who is the receiving wallet, and what money has interchange hands. So that is the basic component of a block, just the data that we are trying to send. Now, we want to obviously make sure that the data is, it's immutable and it can be uniquely identified within a chain. So that's why you have this concept of a hash. So hash is essentially, like I mentioned earlier, like the example with the password, right? So give it any data, even like transaction data, anything. You pass it into the hash, it will always spit out a different unique hash for any input. So that is what we store in the hash. So for a block, we maintain the hash value. For actually the data component, there is generally a block ID, which is like what numbered block is it in the chain. And the nonce, we'll come to what a nonce is. So those three things together become part of the whole data component that we then hash and then use to identify a particular block. That is the concept of a hash. Then you get this is the same thing, a digital signature, which corresponds to. So if you think of it as a fingerprint, it's unique. So every block has that unique value that tells it that, okay, this is the hash that corresponds to that particular transaction along with the nonce and all of that. We'll come to what a nonce is, then you'll understand better what it is. This is just, you'll learn this in the next session where we say that basically we don't want that block to be, if somebody just gets hold of the hash, you don't want to be able to reverse the process and get back the data. So that inverse portion is not feasible in any cryptographic hashing function. It's actually one of the selection criteria for a cryptographic hashing function. That will be explained in the next session, so don't worry. So this is essentially to show how difficult it is to actually try to generate the value back from a given hash. You can create a lookup table to try to say, oh, this value can be then computed to this hash, this value can then be computed to this hash, and so on. But it's computationally too difficult to do that. So that's the sort of concept I want to drive home. When it comes to nonce, I think you'll understand better. Previous hash also I'll just explain before that, which is think of it as it's a blockchain, right? So one block leads to the next, leads to the next. But when we look at the chain, we start from the latest block. So we want to go backwards in history. So that's why we store the previous hash. So we store the hash of the previous block. Then that one stores the hash of the previous block and so on. So that we can traverse backwards in the blockchain. That's why we store the previous hash. So yeah, this is again to show, if a rogue node comes and just edits some content in the middle. So here we have a normal blockchain where the hash of the previous block is stored as a previous hash in the succeeding block and so on. Now, if some rogue actor comes and says, this block, they attack the block and say that I'm changing the transaction values in this block, and when they do that, immediately the hash value of that block changes. So because the hash value of the block changes, it clashes with the hash value expected from the succeeding block. So this previous hash is supposed to be 6B something. that is no longer the hash of the previous block. And so we can determine that, oh, this block has been edited by somebody, and that is a rogue action. So that is why we use the previous hash. So yeah, that's what it's not right. There's some problem, and that can be marked. So that particular history can be marked as, oh, there is some issue here. Now comes to pretty much the most important thing that you have here, which is the concept of a nonce. So let's say that this is our ledger where we are, saying Asha gets so much money, Mariam gets so much money, Arun gets so much money, blah blah blah. We have all this. We have all this data with us. Now we want to create a when we are trying to create a network, we want to be able to create a system where a transaction only gets added to the blockchain when after a certain amount of time and a certain difficulty is attained. Why is that? Why do we go with that approach? Basically, if you think of a blockchain, essentially, let's think that every transaction gets its own block for simplicity. So if you want to trust a block, if you want to trust a particular version of a blockchain, you would trust the version that has the most blocks, which means it has the most amount of history. So we don't want it to be easy for a rogue node or a rogue actor to enter a blockchain, because anybody can start participating in a blockchain. So if they try to join the blockchain and they try to create an alternate history, which is essentially what happened here, right? With this sample, which is some guy has entered the chain and they're trying to create an alternate history where this transaction, maybe he says that I got 1,500 rupees from somebody, but they were supposed to get 1,000. That can be a rogue transaction. So so we don't want it to be easy for these guys to come and make big changes. So we always want that one trusted link or one blockchain chain to be secure and to be guaranteed to be the longest chain that we have. So for that, what do? You make it difficult for these rogue actors to come and make a change. So if you look at SHA-256, let's say that this is the data we fed into SHA-256, this is the hash that is spit out. So you can see it's some random collection of ones and zeros here. Generally, it will also have some other numbers, but basically this is what it will spit out. So what will happen is, now I want to set a difficulty criteria saying that I want you to add some value to this ledger, so that I'm saying, so generally in Bitcoin, this is how the difficulty criteria is set, where they say that so many zeros have to appear in the starting of the hash. So think of it this way: if I just make a change in the ledger and say instead of saying Arun gets 2,500, I say Arun gets 250, the hash completely changes. But think of the possibility of that hash being exactly having 30 zeros in the starting. It's very small, and actually probability-wise, it becomes absolutely infinitesimally small. So before we come to that, so for this value, if you want to find that one value, there might be a couple of values which might satisfy that, but if you want to find those values, it's a very low probability, because you have numbers that lead from 1 till 2 power 32. I think it's 32 bits, basically the nonce. So within that frame, which is 2 power 32 is, I don't know what the number is, it's a very large number. So if you want to find the actual nonce that satisfies this particular criteria, it's very computationally difficult. And actually in Bitcoin, we have this whole process of where the difficulty criteria is set so that it takes almost 10 minutes to mine a block, which is to just get this value sorted. It takes 10 minutes for even like strong as more powerful computers to do it. That is the main thing. You don't want people to be able to make any rogue changes quickly. So you want to slow it down. That's the whole point. So yeah, this is where you have this magic number which gets added. So for this, I'm just taking a random number and showing you that it's a nonce, but we'll have, actually in tomorrow's session, I'll have a sort of sample to show you how a mining thing happens. So I'll show you that in tomorrow's session, because that's more relevant to tomorrow's session. Magic number is what these miners have to do. So what do miners do? They will start from 1, 2, 3, 4. They'll keep adding to this ledger. They'll put 1. They'll see if the nonce is not matching with 30 zeros. They'll put 2. They'll check. They'll put 3. They'll check. They'll put 4. They'll check, and so on. So after so many tries, you'll get to here. So that is why the difficulty criteria is set, and why nonce is so important in think of Bitcoin only. So in Bitcoin, nonce is an absolutely necessary entity that you need to have. And this, the question that was asked earlier. So this is essentially this whole concept of how we are, mining out this nonce. That comes out to be a concept called proof of work. We'll come to that. And that's where that verification of transaction part comes, as to somebody's question would ask. So yeah, why a nonce I've already explained. Mainly the probability of a miner getting that exact particular value, that magic number, in the first try is 1 by 2 power, actually 2 power 32, 1 by 2 power 32. That is such a huge number. It's almost impossible for it to get it on the first try. And that's exactly where the difficulty criteria gets set. So now comes to that, who creates the new block and why? This is exactly the question that I'm not sure who asked. I didn't see the name of the participant, but yeah, somebody had asked that, if somebody initiates the transaction, but what are the steps it goes through before it gets verified and added to the chain? So again, let's meet our 4 old protagonists, Mariam, Masha, Ali, Arun. What happens here is that we have a transaction which we want to initiate. Let's say Arun wants to send money to Ali in this situation. So like we said earlier, anytime a transaction wants to be initiated, it has that nonce value has to be calculated for the new transaction. Let's say a new block is being added every time a new transaction has to be initiated. So when a new block has to be added to the chain, we have to get it mined. We have to get that nonce value mined from the miners. So these 4 people that you see on the left of the screen, those are the people who are participants in this entire in this network, in this decentralized whatever. So let's say it's Bitcoin. They are the 4 people who are participating. Now there are some miners who are just sitting and waiting for these transactions to happen. So we see that now a miner sees that, there is a transaction that Arun wants to initiate to Ali. So what do these miners do? They're all sitting at this thing for this particular transaction to happen. Now how does it go forward from there? So we have, here we show like 3 different miners trying to put different values of hashes and try to find that one golden rule where 30 zeros appear in the first part of the hash for the given transaction data. So all of them are trying. They're all trying different combinations of numbers, and they're trying to find the hash. They're all competing against each other. Now, simple question to ask is, why are miners doing all this work for us? Because it's very computationally expensive to do all of these things. You need to have a very powerful computer with whatever multi-core, CPU, all that stuff. And it's just sitting and waiting for these transactions to happen. So why are they doing it for us? And I mean, if you guys I'm sure all of us are using some banking service or the other. For large transactions, or even in some cases, I've seen for getting your account balance for 10 years and all, they charge you money for it. So why do they? I mean, they charge you money because it is computationally difficult for them to get that data and give it to you. So even banks charge money for certain services. So why are miners doing it? The simple answer is that they also get paid for it. So if they in any network, they have a certain reward available for miners, and when a miner is able to find that nonce value and say that this is the verified hash that I can generate for this block with this nonce, then that miner is eligible for a particular reward, and that is exactly why they participate. They compete for that reward to happen. There are multiple mining farms actually available. You can read about them in China and elsewhere, where there's entire buildings that are set up just to do mining. So it's a completely different industry only, that mining part is. So basically, each of these miners, they try to generate a nonce. That's the first second step that we have to follow. Now, one of these miners has said, yes, I found the solution. This is the solution. Use this nonce and you will get your difficulty criteria sorted. So the successful miner says, yes, I have the solution. Here you go. So actually, in blockchain terms, this is called a cryptographic puzzle, and they have solved, and the successful miner has solved it. In other key points, notice this difficulty criteria will change over the course of actually, I think in Bitcoin it's about 14 days, and they keep changing it. I'll come to that at the end anyway. So now successful miner says, cool, I've got this hash value. can we move forward with the transaction? He sends that out to this guy. Again, same thing, that 30 zeros. Have you got the 30 zeros? Solution is what they'll check. So miner can lie, why not? So the all of the participating nodes, they go and check whether this is a valid hash based on the difficulty criteria set by this decentralized network at that particular time. So in this case, I'm considering 30 zeros at the start to be the deterministic criteria for this. So at that point of time, you if it is 30 zeros, and there is this whole consensus mechanism where at least the simple majority of people have to agree that this is a valid node. So all of the other people, as I said earlier, the 4 people maintain copies of the ledger. All of them have to agree that this is a new valid block. Then only that valid block gets added to the blockchain. So they say that, okay, this is the new block. The miner says, please verify it, and they just broadcast the whole thing to everybody. And like you're seeing in this picture, all 4 of the participants we have, they all maintain one copy of the exact same ledger. Now, what each of them do, they will wait for the verification. They will try to verify if, yes, this is the new block, this is the new block, this is the new block. They'll compare against the difficulty criteria. The miner will sit and wait for that particular verification process to come, because otherwise you will not get his reward. Then one of them says, yes, this is the successful block. Then what happens is that the miner gets paid a certain number of, so LD, I'm just mentioning as ledger dollars. Generally what happens, you get paid, I mean, if it's Bitcoin, you get paid in Bitcoin. If it's Ethereum, you get paid Ether, so like that. So the miner gets paid a certain amount of money for finding that hash value and for participating in the mining process, basically. So that value is preset generally. So the network tells the miners that, you can expect this much reward for finding finding the right nonce and saying that this is the new block that has to be added. Then, yes, this is essentially the process. So what I've actually described till now is actually the proof of work. So proof of work is what really drives home the point that that it maintains the fact that it is computationally difficult to find out the hash, and it maintains a trail of knowledge to know that, okay, which miner has got the right solution, whether all of the participants or the simple majority of the participants, which is a 51% thing, whether they've all agreed to the transaction, and whether that block got added or not. So this hash less than the target, that is basically there is actually a slightly small change in Bitcoin where there is so when you generate that magic nonce value, it has to lie within that 2 power 32 number. Sometimes that is also changed. So if it does not lie within that target number, then some additional change is made to the data that has to reside in the block, and then they try again. That is, extra computational difficulty that some blockchains add, like Bitcoin does. But let's not go into that. Let's consider the simple solution where just be less than 2 power 32. Just that. So that is the last check it does. If yes, then yes, cryptographic puzzle is solved and new block is added. Blockchain continues to grow. So another block gets added, another block gets added, another block gets added. And because you're making it computationally difficult to add a block, it makes sure that the longest blockchain is more likely to be absolutely correct and absolutely valid, because you're going through all of these steps of consensus, everything. So that is the main thing here. So yeah, this is just, think of it as, you're mining for gold, but you're mining for Bitcoin. So that is essentially where this whole proof of work concept comes. So that how you verify a transaction is essentially this whole process that I've just gone through in a very overview sort of way. We'll have a slightly more visual demo of this tomorrow. I'll be showing one part. Then, new block, all of them say, yep, this is a valid block, but as you can see, that little link has not been added. No? So to add the link, what do you need to do? The previous block hash has to be added to the new block. The new block has maintained the previous hash. So the previous block hash has to be added there. All of these fellows, participants, they do it and they add it into the chain. So now you have a new block in the chain with 4 blocks. That's essentially how the whole process goes. So this is the whole thing about, mining, verified, rewards, all that stuff. So mining is the step that we defined where all the miners they struggle to get the verified block. They submit it for verification, they broadcast it. Once they get that consensus, they come back, they say that cool, you've done the right job, you've got the correct block. Okay, there is a question here. What happens if there is no norm? Why to have this complex part in blockchain? I think I've largely explained that. This is the whole point is that we want it to be computationally hard for it to be for anybody to make a change in the blockchain. That's the whole point. To add a block, we want it to be computationally hard. We want it to be difficult for the current world state of the blockchain to be changed. That's the whole point. I hope I've answered your question. If I'm not, please put it in the chat. I'll try again. So we've gone through the three things that are happening. The reward is finally what the miner gets, saying that you get so many Bitcoin, Ether, whatever, for completing the transaction. So this is again just similar sort of example for the same thing. I'm not going to go through this again. So this is just like saying that this is the amount of money that somebody could get and all that. And then obviously at the end of it all, again, even the fact that the miner gets paid has to be is also recorded in the ledger. But because that is in and of itself a verified transaction, that part again is not verified and put in. There is another mechanism used for that. We won't go into it. But just think of it this way: every single thing is transparently visible to everyone. That's a very good thing that happens in blockchain. So these are just a few thoughts that I had, questions. So I'll try to finish it up as ma'am had requested, another 6-7 minutes. I'll finish this, then I'll completely open up for questions. You can ask anything you like. So this is something that I mentioned in the when I was explaining the proof of work. So that target hash or the difficulty level, which is saying that 30 zeros. So how often is that changed, or is it changed at all? So the answer is yes, you do change it. So this is actually showing this is a Bitcoin scenario. So what happens is every 14 days, they change the difficulty level. It's adjusted slightly. So that 14 days is not arbitrary. So that value is actually calculated based on the time required to create 2016 blocks. Now, the 2016 blocks value is arbitrarily been selected. They're just saying that, okay, 2016 blocks, it should take this long for you to add this many blocks to the blockchain. So in our example, we were only adding one transaction, one block was getting added. In this, what happens, they match it out so that, so many blocks don't get added. The computation is difficult, right, to add blocks. So that's the whole point. One more thing that you can, if you're, I was quite interested to find out, how they calculate this difficulty level again the next time. So let's say we are at the end of 14 days. Now, how do they calculate this difference? So the first main criteria that they use is that they want a minimum of 10 minutes to be taken to add a new block, to mine and add a new block. They want 10 minutes to be taken at the very minimum. So what they do is, they have, so that translate that into number of seconds. So what they actually do at the end of 14 days is, they take the amount of seconds it took for a block to be added in real time, and the amount of seconds they expected it to take. So, and they divide that up, and they get a ratio out of it. That ratio is proportionally used to change or alter the difficulty level. So think of it as if the miners were extra good, then the difficulty level was too easy for them, and they were doing it very quickly. So let's say it was supposed to take 10 minutes per block. Instead, it takes 9 minutes per block, or 9.5, or 9.75 minutes. Then what happens is, these guys, they'll increase the difficulty level a little bit based on the ratio of the time taken for mining all of these blocks. Then we go to this guy. What is it? If it's the case where if the miners are struggling left, right, center to try and find the miner, to find the particular nonce, and to say, okay, this is a verified block and all that. So in that situation, the difficulty level will be slightly decreased, but that rarely happens. Generally, it's always an increase only. So that is where the target or difficulty level is changed. Another sort of query that took is just how long does it take to create a block? So the time that they monitor, right, to set the difficulty level, that is really the time that it takes to create a block. That's where they go towards, this is the actual, internal part of how Bitcoin does the changing of the difficulty level. Who all can create a block in a blockchain? I think I've already sort of answered it in the general presentation, but basically anybody who is, has that computational capacity to sit and say, okay, I'm going to sit and listen for transaction requests. I will mine the nonce and I will try to create a block, try to create a verified block. So with every particular transaction, there will only be one successful miner. So that is the underlying, basic criteria, that only one person becomes successful and only one person receives the reward at the end also. So that is who all can create a block in a blockchain. So what is the concept of a blockchain? That ensures that data cannot be altered by any of the users within the network. Maybe you can put it in the chat. So it's actually we've actually dealt with this in the presentation. So does proof of work enable that data cannot be altered, or hash encryption, or public distributed ledger? The very concept of it. So which one is it? Yeah, I would say it's a combination of B and C, but Shweta in the chat says hash encryption. That's correct. So as we said, that the hash just cannot be changed. It's a combination of hash and the public distributed ledger that gets combined. Yeah, C is also, I won't say it's wrong. It's a combination of both that becomes proof of work. Doesn't really ensure the data cannot be altered. So that's something different. I see another question. In the blockchain, if an attacker changes the hash value of a block in a chain, it could be identified that the previous block is invalid. But how could it be recovered? Okay. So that's a very, very interesting question. Let me just go back to that slide. Okay, next slide goes to great. Okay. So actually, I will not this one. I'll show this slide. This will probably be quite clear about that. Yeah. Okay. So now we have a very simple situation, right? Where we have 4 members, and these 4 members are all keeping a copy of the blockchain. So if a rogue node, like let's say the person on the top right is a rogue node, and they add a rogue block at some point. Okay, and this is after going through the consensus mechanism, all of it has somehow gone through, and then we realize that it's a rogue transaction. Another large case of scenario where the transaction itself will not be rogue, meaning that the transaction was verified by the sender, but it was a fraud. So there is a sample of that. Actually, I can give you an example, which is recently on about 5-6 months ago, I think, or more than that, maybe a year ago. There was on Twitter. What happened was somebody hacked into a lot of very famous Twitter accounts, which was I think Elon Musk and Bill Gates and all these kind of people. They logged into their account and they said that because of the pandemic and everything, because everyone is struggling, I'm doing a giveaway or something like that. And they said that if you send me X number of Bitcoin, I will send you back 2X number of Bitcoin. They had a scam like that. So people are, they thought, oh, wow, and they gave a wallet ID. Now, as I said earlier, you don't know who that wallet ID belongs to. It's all anonymous. So people started sending money, thinking that it was actually Bill Gates. And they sent money off. And then what happened? The blocks got added, all of it happened because it's a verified transaction, right? Because the sender has said, I want to sign and send it. The receiver is happily going to accept all the money. And then there is this whole concept of Bitcoin washing where you can, convert even that dirty money into clean money and all that. That's a different thing. But so they did that. So now what happens? What you can do is you can actually revert back to a previous state of the blockchain based on the copies that all of the other guys are maintaining. So that particular update may not have happened in all of the other blockchains. So even if one of these guys has a rogue copy, the other world states that the other nodes are maintaining can be used to replenish the rogue one. And that becomes your new world state, which is the world state that you think is, completely verified. So I hope that answers your question. When will a new block be created? What is the size of each block? Okay. When will a new block be created? And both of those questions actually, that depends a lot based on, okay, raise hand one I'll just take after this in a moment. So a new block is created, that it depends on the network actually. So the size of the block also changes with the network. Generally, what happens is when a new block is created is when the next transaction cannot be accommodated into the same block. So that's generally where a new block gets created. That changes with each network, but that's the basic concept. I'll go back to that page I was on. Yeah, somebody had raised hand, so I don't know who it was, but somebody raised hand.
Can I come in?
Yeah, please go ahead.
Yeah, see, there is a limit as to 21 million is the maximum size of bitcoins that can be mined, right?
Yeah.
So if all the bitcoins are mined, maybe in near future, then what will happen to the miners? They will stop mining because they will stop getting the reward, right, for the mining.
Yes. So that is, that's not entirely wrong. There is a limit up to which there is, they say that there is a theoretical limit up to which then that Bitcoin can be mined. To be honest, I don't really know the answer to that question. It's something that is it's something that people are raising questions regarding Bitcoin, along with its environmental concerns. With the amount of energy it requires to actually mine the Bitcoin is much larger than it's much lesser than the amount of energy that it uses is much larger than the amount of money.
Yeah, for that they are shifting to proof of stake. Actually, they are shifting to proof of stake.
Bitcoin doesn't really have a proof of stake way of doing it. So that's one major drawback that it has. This is the other one where so if the intrinsic value of the coin doesn't last, or if the number of coins available doesn't last, then the livelihood of the blockchain may not last as long. That's completely valid. So yeah. There might come a day where miners may not be as many miners that participate.
So they may increase the difficulty level and they may go on increasing, but they cannot delay it for long.
Correct. That is the whole problem, because see, the minute you increase the difficulty level, the amount of processing power that you have to use, the amount of different combinations you have to try to achieve that one verified block becomes more and more and more. So you become like a slave to the farm that has been set up in China or in all these European countries, where they just do this for a living, where they just mine for a living. So it becomes completely. I mean, then again, you almost become, you become completely beholden to them at the end. So that these are like fundamental problems that exist with Bitcoin, which is why recently the value has been fluctuating a lot. If you look at the trading and all that. So yeah.
I would like to add here to say that there is on Thursday morning a topic on research topics in blockchain. Okay. So this, what Hemant is talking about, the difficulty level increasing, how much time to keep it and other things, how much time should we give it for mining, how long should you wait? And another problem would be that when there is a computational power itself increased within the client end systems. For example, if you have, let us say, a highly computational powered machine, which means, for example, let us say things like quantum computing, etc., is used to generate that nonce won't take much time. So, like as Hemant was telling, this is exactly the problem that's happening. There are China farms, dedicated for that. So these are all open-ended research problems that will be covered on Thursday morning. Okay. I was trying to answer the question to whomever was asking the question. Sorry for interrupting. Go ahead, Hemant, please.
Yeah. Please keep asking your questions. I have a couple more slides to go through. I'll just keep going through. In between, please interrupt me if you want to ask a question. No problem. What about private key management? Okay. So I'll give you an example from, let's say you set up an EC2 instance or something like that on AWS. You are given a PEM, a private key actually, that you maintain locally. That you are completely responsible for maintaining that private key. If you don't maintain that private key and somebody gets access to it, anybody can unlock messages that are coming to you. Any malicious actor. But again, still here, because any messages you send, you cannot unlock yourself, as I mentioned earlier. Only the messages that are coming towards you will be able to be unlocked by somebody with the key, with the private key available. So that part comes down to individual management. You have to do it yourself. That's where the private key management comes in. Okay. Yeah, this is again the proof of work is to, as I explained earlier, you want to maintain the fact that the longest chain is the one that's selected and all that. So miners receive a reward, all that stuff. Yeah, so this is the conflicting world states. As one question was asked, where you can, you revert back to the previous state that you want to use. And if there are you always try to select the particular blockchain that has the most number of nodes, as I mentioned earlier. Those are the two things that go through in a conflicting state. So this is just further explanation of the sort of proof of work and how it's really enabled us to move away from a central authority having to verify that the current world state is valid or not, and you trust that the work that has gone through before the process of verification is well and true. That's basically where this comes in. I mean, I won't call it assignment, but like things to look at is just a bit of thought. So these are like actually these are not the highest on the if you check on CoinMarketCap, these are not the highest valued, but Bitcoin and Ethereum are the highest valued. Ripple, Litecoin, Ethereum Classic, all of these are other Bitcoins that exist on that you can see as coins that exist on the cryptocurrency market. This is quite an interesting book, The Truth Machine. So they look at how blockchain could shape our future and why it's really necessary in today's world, and very interesting. And I mean, if you've read this book already, it's a great read, written by Michael Casey and Paul Meany. So very good read if you're looking at it. So yeah, I mean, that's basically all I had to show today. Any other questions you have, you can ask me. You can either ask in the chat or you can ask by unmuting yourself and go ahead.
Hemant, I presume you answered the questions in the chat, right?
Yeah, I'm looking at the chat.
Okay.
Yeah, so if I've missed any question, please just ping it again. But I think I've gone through most of it. Okay, so there's another question. Assume if there are 10 members participating in blocks. If 11th member wants to participate, whether he or she will also get all the previous blocks in the chain. Yes. So every new participant has a copy of the current world state of that blockchain. So the entire chain they maintain. They don't, it's not like you start out from it's not like a Git branch where you fork away from that and you continue. So you get a complete part of that chain. So it's for the benefit of the new participant actually, where you want to know, you want to trust the network before you join, right? So it's essentially for that one. And every transaction you do, you want it to be added to the same trusted network. So that's the idea for having the other blocks also participate. I mean, all the blocks become copied over to that person, the new participant. It's a good question. Thank you. Any other questions you can please ask?
I have one query.
Yeah, please go ahead.
You told that wallet address is known to all, means if we talk about a public blockchain, so that address is known to all, means who is doing the transaction. But these days we are talking about anonymous communication, also privacy enhanced technologies. So how it can be incorporated in blockchain, means is it possible if we are not talking about some kind of anonymous blockchain like we have Monero, which claims to keep the privacy of the transaction? So is it possible, this anonymous communication in public blockchain?
Okay, so that's a good question. So I've given an example of that Twitter scam, right? So why it is so hard to trace these Bitcoin scams is that So if somebody just said that, oh, I'm Bill Gates, I'm going to give a doubling amount. You send me X number of bitcoins, I will give you 2x bitcoin. So why did that work? Because there is no way to verify. And in the tweet, he just mentioned a Bitcoin wallet ID. And people just send money to it. No, there is no way for us to verify if that wallet ID belongs to whom. So in essence, you already have some level of anonymity within the current implementation of public blockchain as well. So that part really goes. I mean, you already have that level of that level of security from a privacy standpoint. So the only thing that I think that you would get in extra from Monero, if I'm not wrong, I'm not that familiar with Monero, but I think what you get is that you do not. So if the other people, the broadcast people, do not know who are the wallet IDs as well. If you're aware of that more than me, if I'm making some error here, please correct me. But this is my understanding that broadcast portion there, you don't have a. So in the example we showed, that Arun and all those 4 people, if Arun wants to send money to Ali, here Arun won't be there. It will be a what do you call it? It will be a wallet ID. So the wallet IDs are visible to everybody on the network because it's a broadcast. It's sent out to everybody. The miners can see it. Everyone can see it. What happens on Monero, at least what my understanding is, that they obscure that also. So nobody can see the actual wallet IDs. So there are some use cases for it where, if you want to transact money in even increased anonymity, where you don't want, there's a whole problem with all this taxation against Bitcoin and all that. So with all those kind of stuff, people do want more anonymity with regards to their transactions, and they don't want people to know about it. So there is a use case for Monero, but I think that goes a little too deep, in my opinion. So public blockchains have this way of doing transactions where you provide the anonymity via the fact that the wallet ID is not directly linked to your name, basically. I hope that answered your question.
Okay, thank you. So means you are saying that wallet address is not binded to identity in a normal public blockchain also.
Yeah, it's not bound to the identity. But I think the key differentiator between a normal implementation of a public blockchain and Monero, in my understanding, is limited, admittedly, is that the broadcast portion also is anonymized.
Okay, so means identity is not linked to wallet address in normal public blockchain also.
Yeah, it's not linked to you. So if you set up, I think in one of the sessions you set up even a wallet in Ether, you just can. So there you will there's no way to track that there's no email ID or there's nothing linked to it.
Okay, because in normally public key we do have email IDs linked to it. So
right. You will not. Nobody will be able to trace it. That's the big problem that governments are facing with the regulation. That how do I regulate against it? Right.
Yeah, that's it. Okay, thank you very much. Okay.
Yeah, no problem. Okay, there's a question in the chat. If the anonymity is maintained...
1 minute, Hemant. To the person who asked the question now, we are setting up a digital wallet as a hands-on session on the 4th day, ma'am. That is Thursday, okay? So when you attend that session, you will understand better, ma'am. Tarun Preet.
Okay. Thank you, ma'am.
Yeah.
Okay.
So there's one more question. If the anonymity is maintained about the sender and receiver, then how do we track if transactions are made for malicious activity? Okay. So, I'm assuming that question is keeping the part where let's say the proof of work has all gone through, then how do you track for machine malicious activity? Or I'll consider both cases. The proof of work part is able to capture all of the malicious activity. So, if somebody is, if a person tries to alter the blockchain itself and say that, I received so much money from this person and initiate a false transaction, I think I've explained in the slides, how that the whole process of the verifications and all of that, and adding a digital signature, message ID, and all that stuff is able to counteract against that. So I think that part is covered. So now in the proof of work portion, we have to go through that 51% consensus mechanism for a new block to be added. There also we have a slight check against any kind of malicious activity to be done. Now, third case is the block has been added also, like the Twitter case. Then how do we track for malicious activity? Now, this is largely where the whole legislation problem comes into play, and it becomes quite hard to track malicious activity, because how do you classify malicious activity? Somebody has to report that, oh, this is not a valid transaction, and then that has to go through a whole process of then the participants in the blockchain can decide whether or not to accept a certain version or word state of that blockchain and revert back to the previous one or all that. So all that comes into play there. So I hope that answers the question. If not, please think. I will try again. Any other question? I think we are at time also. But please, if you have any questions, you can go ahead.
Any questions? Okay, if you don't have any question, on behalf of Information Science and Engineering Department, MSRIT, I would like to thank you, Mr. Hemant H. Kumar, for your introduction session to the blockchain technologies. Your way of introducing the topic covering the evolution from clay tablets to palm leaves to paper to today's digital era was unique, and it is interesting. Okay, you gave a very fundamental approach to understand the technologies involved in blockchain, such as components of blockchain, hashing, model of a blockchain, framework, etc. Thank you very much once again for Mr. Hemant Kumar for your valuable time. Thank you, Hemant.
Thank you, ma'am.
Thank you.
Thank you for all the participants to be so inquisitive and to ask questions. Please keep this enthusiasm going for all the other speakers. I promise you that they will be very knowledgeable in these subjects, and they will be able to give you very good answers to your questions, and they will try their best to give you a good experience of this activity. So I really encourage you to ask questions. There's no bad question. There's no stupid question or anything to ask. Please ask away. This is completely for your benefit.
Thank you,
everyone. And I think it's your lunch, right? So enjoy that. I'll go have mine.
Yes.
Yeah, and one more small thing, like the speaker is coming back again tomorrow. I think when Hemant?
Tomorrow I will be there, session 2 and part of session 3.
Right. So Pratima, you can take over.
Yes. So all participants, I'll request everyone to join for afternoon session. That is third session from 2:30.